Okay, in this part, we're going to look at finding limits algebraically. And so it may be one that's a little more difficult than the one we had in the last section. So we'll take a function, we're trying to find the limit as x approaches -1. And then I would say when you look at these kind of problems at first, kind of their non-factored form, we want to come up with a limit for this guy. When we're looking at it, you might not immediately look at the denominator and say, hey, maybe -1, is that a number that I can or can't put in there? But we're going to try a couple different methods here, so we'll notice this regardless. Sometimes it's way easier to see if you have the factored version, which don't worry, we'll end up doing at some point anyways. But I'd say like all of them, a good place to start is look at the graph so we can get a picture of what we're dealing with. And because if you're spending the time to type the function into your calculator, you also can go to the table and kind of explore it numerically. I don't know if I've mentioned this before. If you have a T84 and it has a new operating system, you don't have to do this. If you want to type in this function as like a fraction divided by another fraction, but then you need parentheses around the top and bottom so it knows what's the top and bottom. But if you see these little green F1, F2, F3, there's a little sub menu built in. So if I want a green button, I hit the green thing first and I can pick fractions and mixed numbers. I'd say what that really saves me when I go to type in a function like this is I don't need all those parentheses to tell it now that it's the top and bottom. It actually makes a fraction look like a fraction. If you have an 84 and it doesn't do that, get a hold of me because they have the new operating system on, new, maybe like 10 years ago. They have it online for free. You can upload it on your calculator. If you have a free calculator you borrowed from the library, it should already have it because I updated all of those quite a few years ago. Anyhow, just a side note about things that can save you some time. So let's hit graph. All right, it looks like we can definitely see at least one vertical asymptote on this. So there's some number we're not allowed to plug into this function. It kind of appears to be maybe around -5. It's hard to tell. We can go to the table. Not that that's the number we care about, but like I notice we can't plug in -1. So that must also not be in the domain, right? That causes us to divide by 0. And -5 causes us to divide by 0. So we can't just directly take the point, or we can't do like we did in part 1 where we just plug in -1 because we'll end up with 0 over 0. And so, but is there something else we can do? So one thing we like to explore sometimes, because you can kind of see, even on the graph, like you don't have to do it this way, but that I can't plug in -1, but I should be able to get really close to -1. Like if I plugged in -0.999, I get something around 1.24-ish. So I still can explore what happens when I get close to -1, even if that is an open point or like it's called a removable discontinuity. We'll talk about that more later. So we'll go to the table, then we'll go to table settings. Right? We don't want it filling in 1, 2, 3, 4, 5. We want to use some specific numbers here. So we'll go like -0.99, -0.999. We know we can't do -1. And then we'll try -1.0001, -1.001. We're just getting closer and closer. And it kind of appears, sometimes it'll do this, right? There's still other decimal places here, but it runs out of room. So it's just kind of saying it's so close to 1.25, it seems to be rounding to 1.25. And it seems to be doing that on both sides, right? So it does look like as x gets closer to or approaches -1, it looks like y is approaching something like 1.25. But what we like to be able to do is maybe show that algebraically. And so one of the next easiest types to do algebraically is hopefully something cancels in this. So there'll be other types, but another reason I like graphing it and looking at the table is it's nice to know there's an answer before you start trying to do it algebraically. Like you already kind of know what the answer you're shooting for is. It looks like it's somewhere around 1.25. And if you don't see like there's a limit, then you don't spend a whole bunch of time kind of spinning your wheels in the algebra trying to see if you can get it to work. So I would say first thing I would do on something like this even if we hadn't done all those exploration steps first, is factor the top and bottom. Like I said, it makes it easier to see if there's something you can't plug into the bottom. And it'll be way easier to see if there's something that cancels, right? Because if you're trying to cancel in a fraction, you need it to be a factor of the top and bottom, meaning multiplied. So I can pull a 5 out of 5x and 5, and then our good old FOIL. So I know the only way to get x squared is x times x. What multiplies to 5 but adds to 6? So maybe 1 and 5. And if you're doing the guess and check type foiling, don't forget to check, just kind of quick foil that in your head and make sure, yep, it multiplies to 5, adds to 6x for our middle term. And now we can see it does look like there's a common factor that will cancel here. So x plus 1 is a factor of the top and the bottom. And so what we've just done is turn this into a limit where we can plug in -1, because now our fraction just looks like this. And so now where there used to be an x, we'll put a -1 instead. Right, we couldn't do that before because we'd get undefined, so we'd be dividing by 0. And it looks like we end up with 5 over 4, or kind of like we thought, 5 over 4 as a decimal is 1.25. And so there you kind of have, you already knew the answer before you started, now you have verification that it works. And I don't know about you guys, but I find it weirdly satisfying when the algebra works out. The longer the algebra is, the more satisfying. We'll see some later with square roots that are quite fun when you get them to actually work.